Bueno. Ya, este funciona. Este tiene audio y todo. No lo pongo. Bueno, sí. Professor Demelo, we are ready to start.
Great.
Ian is going to give the introduction and then we'll continue with the slides. Thank you.
Hello, my name is Ian Foltz. I'm an adjunct professor or assistant professor in electrical engineering. And it is my pleasure to introduce David, and he will be presenting his research and defending his dissertation. Other people on the committee are Jürgen. And it's my pleasure. Jürgen Kossel is his co-supervisor. Professor Siggy is his, has also provided lots of other good information and help, especially in fluid mechanics. And his external examiner is Professor Andrew DeMello. Dave?
Thank you. Well, thank you all for coming to my presentation. I'm very glad to see a full room. And today I want to tell you a story of how droplet microfluidic systems have used little droplets to create chemical reactions for the production of advanced materials. And by advanced materials, I mean nanoparticles, quantum dots, spherical agglomerates, and even gene products like proteins and enzymes. So the problem of these technologies is that they have a very limited production volume. So they are only useful for laboratory settings or experiments, but when you want to bring them to a commercial stage, then it's difficult to scale them up. And today I want to show you how I made this device that can produce commercially relevant scales of production of these droplets. So let's start. This is the outline of my talk. I'll give you an introduction to microfluidics. Then we're going to discuss some of the pharmaceutical manufacturing and how it's done and how can we improve it. We're going to discuss some droplet generation geometries and select one for parallelization for scaling up. Then I'm going to show you the device which scales up the droplet production, some monitoring sensors, future work, and finally conclusions. So, introduction to microfluidics. Microfluidics is a science that deals with the behavior, control, and manipulation of small quantities of fluids, typically in the range of microliters to picoliter in size. So, to give you an idea of what is these volumes, if you take a cube and the length A, if the length A is 1 millimeter, then you have a microliter. If A is equals to 10 microns, or 10 micrometer, then you have a picoliter. So this is more or less the range that we're going to work with. So this is to put into perspective. So a human carries 100 microns, then you have cells that are from 1 micron to 100, and you can go inside the cells, there is chromosomes, and then you have DNA base pairs. So this is where microfluidics live. For the physics guy in the room, this is where MEMS live, and nanotechnology. So nature has been wiser than us for many years, and this is no exception. Nature knows that at these microscales, nanoscales, chemical engineering and microreaction is much more efficient, and this is why it has stored all the information of our lives in these DNA base pairs, in DNA, which are in the nanoscale. So microfluidics is a multidisciplinary field. It involves medicine, chemistry, biology, mechanical engineering, electrical engineering, and microfabrication. So we want to use these engineering technologies in order to develop applications in these areas. And these give birth to what we now call lab on a chip, which is the integration of these technologies into applications in biology and chemistry. Microfluidics for chemistry brought what we now call flow chemistry. In these type of reactions, you have a microchannel and you have two chemicals. They join in this intersection, and as they flow through this microchannel, the reactions happen. This is different from batch chemistry, in which you have containers, and then you have to add your chemicals and produce products. So the difference between these technologies, apart from the configuration, lies on the scaling laws. So volume scales to L cubed and surface area scales to L squared. L is the length, the characteristic length. So you can imagine when you pass from this macro scale to this micro scale, you have a length reduction. So to put this into perspective, a 10 times reduction in length will give you a 100 times reduction in surface area and 1,000 times reduction in volume. So for things like heat transfer, which is a phenomenon based on surface area, it's much more efficient in the microscale. And for things like heat storage, which is a phenomenon based on volume, is much better at the microscale. So surface phenomena becomes more important in the microscope. So let's do a further comparison between these two technologies. So we can see that batch technology has limitations in performance. And this is because heat and mass transfer, which are important in reactions in general, are limited because of the big volumes. Whereas in microreaction technologies, heat and mass transfer are efficient because of the surface area, and you can achieve much greater control. However, there is also another important comparison, which has to do with the scalability and the cost. The way we do chemistry, normally, it's much more cost-effective, and you can scale it up to wider production volumes. And in microscale, well, you have very limited volumes, right? So this is what we are going to try to target in this presentation, this thesis. So microreactors, there are two types. The first one are single-phase microreactors. In this type, you have two fluids that are miscible, and they join this junction, and then reaction happens downstream. The mixing occurs by diffusion. Multiple step reactions are simple because you can add more junctions, and then you can add multiple step chemicals. It has simple fabrication requirements. However, there is a problem with these technologies, and this is the flow profile. So if you look, this is the top view of the channel. If you look at the flow, we'll have this distribution. The velocity of the flow will have this distribution. So in the center, the velocity will be maximum, and at the edges, the velocity will be very close to zero. So fluid elements that are in the center, they will travel faster than the ones that are in the edges. So this brings problems with the residence times if you want to use this for reactions or chemical reactions. And then you can have clogging and fouling of your devices because some byproducts of your reaction may get deposited on the channel walls. The second type is two-phase microfluidic reactors. And here we use two immiscible fluids. One is oil, one is water-based. And then you generate droplets. And inside the droplets, reactions can take place. So there are two types. One that is called droplets, the other one is plugs. And the difference between them is just like the droplets, they don't touch the walls, and the plugs, they touch the walls, and because of that, they have internal circulation. The advantage of this is that you have now discrete volumes, and they move at the same speed in your stream. And so you can have like consistent residence times, and you have other benefits, which has to do with control of the size and shape, and narrow distribution, reduce clogging and fouling problems. And some of the issues that this technology brings is the multi-step reactions are a little bit more challenging, but possible, and low production volumes, which is like the thing that I want to address. So this thesis will be focused on this type of two-phase microfluidic reactors because they have more advantages than the other ones. So what is a microfluidic droplet generator? So a microfluidic droplet generator is a system comprised of two channels or more channels, and they have a junction. In this junction, two fluid phases meet and interact. We have the dispersed phase, or the phase that will be cut into droplets. And then we also have a continuous phase, which will be surrounding these droplets. So you are generating an emulsion. If the dispersed phase is water and the continuous phase is oil, you have water in oil emulsions, and you get oil in water emulsions if you get the opposite. So there are some important forces that actually are responsible for this droplet formation, and you can characterize them with these two-dimensional numbers. The first one is the capillary number, and this capillary number relates the viscous forces of the continuous phase, which is this one here, tension between the two liquids. And it is given by the velocity of the continuous phase, its viscosity over the interfacial tension. The second one is related to the dispersed phase, or the inner liquid here, and it relates the inertial effects over the surface tension. And this is the equation. So applications of this technology can be found in different areas. We start from polymer particles, then we can see nanoparticles, quantum dots, microcapsules, and active pharmaceutical ingredients. So, one of the things that all of these researchers have stated is that we have come up with this nice system that produces very efficient materials, but then you should be able to scale it up if you parallelize these devices. However, this statement is not as simple, and I'm going to tell you why. So let's start by the pharmaceutical manufacturing, how pharmaceuticals are made. So it's actually the thing that you find in the industry is an Asian technology that has been optimized, but it's still an Asian technology. So you start with your crystals. API means active pharmaceutical ingredients. You start with your crystals, you grind them, and then you mix them with more chemicals, like they are called excipients. Then you dosify, do a granulation, and then you put it into tablets. So this is like playing with candy in a mortar, like you're trying to mix things. The problem with this is that when you look at the microscale of these powders, you'll find that some of the particles will be very big, and some of them will be very small, like this one, or in all these cases. And when we plot this, this is probability density, which is how many particles we find, and this is the particle size. So you can see that most of the particles are small, but then you still have very large particles. And plotting this into a log-log scale, like you can see in this curve, you have a nice belt distribution curve, but then again, like, the dispersion is 2 orders of magnitude wide. So why does the size matter in pharmaceutical manufacturing? So size matters because of 2 reasons. One is transport, which I'll give you this example. So dry powder inhalers are these guys. They are used to treat diseases such as COPD, or chronic obstructive pulmonary disease, that affects over 330 million people around the globe, or asthma. And so in these dry powder inhalers, the powder has to travel through the mouth, through the throat. What is this? What can I do? Okay, let's continue. So the particles, they need to travel through the mouth, through the throat, and then reach the alveoli. The alveoli are little sacs that are at the end of the bronchia, of the bronchus. So particles are large, from 5 to 10 microns in size. They get deposited in the mouth. Particles that are intermediate, like from 1 to 5, they travel efficiently to the alveoli. And particles smaller than this, they fail to deposit and they are exhaled. The other example of why size matter is dissolution. Right? Let's say this is a particle, a drop, and you want to dissolve it. So the dissolution is given by this formula that is called the Noyes-Queeny equation. And it describes the dissolution rate is equal to the area of the particle, the dissolution coefficient, over H, which is this layer that you can see here. And then times the concentration gradient. So this equation states that the dissolution rate depends on the area. And then looking back at our particles, so we have particles that are very big and others that are small. And the smaller particles can dissolve 10 to 100 times faster than the big ones. So this is like a lot of time comparison. Like, imagine you have a particle that dissolves in 2 hours, and then another that dissolves in, I don't know, 24 hours or 20 hours. So a comparison could be made with sugar. So it's not the same time that it takes to dissolve sugar in grains than the one that it takes to dissolve a cube. Size control is extremely important for low water solubility formulations of drugs. And this is because from the newly developed pharmaceuticals, 90% are in crystal form. And from these, 90% are low solubility, which means there is a huge problem with water solubility here. And then 40 to 50% of these drugs or drug candidates, they don't go further investigation because they're low solubility problems. So how can we improve the solubility? So there are 2 ways. One is to control the size and distribution of these particles, and the other one will be to control the core formulation of your pharmaceuticals. And we can do that with microfluidics. So let's look back at the pharmaceutical manufacturing. You have this process that has this distribution in the pharmaceuticals. So the question is, can we engineer the size of the crystals so that we can improve the pharmaceuticals and their efficiency? And the answer is yes. We can use droplet microfluidics to have little distributions with a controlled size. So we can have particles of 100 microns or 10 microns. And then we can also control the size, and we can control the formulation. We can have a combo formulation, which means that you can have 2 drugs inside these particles. How we achieve this? So droplet size control. We can control the size of the droplets by few parameters. One is the dimensions of your device. So if you make them smaller, then you'll have smaller droplets. The other one are the flowing rates and the flowing rate ratio, which is how fast you send the liquids through. And you can have possible droplet size between 5 microns to 1 mm, although smaller particle droplets have been made. So then we can use these droplets as a discrete templates for drop crystallization. And the advantage is that we have a control size, we have a precise composition, so the formulation will be the one you want. You have a narrow distribution, and you can control the morphology. So let me tell you how drop crystallization occurs. So you have a droplet generator that is making droplets. Then the emulsion, which is the composition of the continuous phase and the droplets, it's spread into a surface, and you form a thin film. And then you apply heat, and there is an evaporation. So your emulsion first has this size, and when it evaporates, it shrinks down and gets like concentrated. When you reach a supercritical concentration, a nucleus will form, and then followed by crystal growth, and then this droplet will be consolidated into a particle. Some examples are crystals that look something like this. You can see the narrow size distribution, so all of them are with the same similar size. We can also generate co-formulation, like in this case, where we have a combo of 2 pharmaceuticals. So you can see that these droplets, they look, or these particles, they look like golf balls, and this is because they have chemicals inside. And then you have control of morphology. And by control of morphology, you can have these different parameters. So when you change these parameters, a single crystal can be crystallized, a single substance can be crystallized in different morphologies. For example, you can have alpha crystals, gamma crystals, and spherical agglomerates. For pharmaceutical companies, what they are interested is in this type of spherical agglomerates. And this is because they have surface characteristics which increase their surface area, and they dissolve faster. So why these methods are not useful to produce commercial products? Well, the answer to this lies in that it's not economically viable, because one of these devices, they can only produce 10 milliliter an hour. So it's very little the production. And we cannot use traditional chemical scale-up, which will be like making it larger, because that doesn't really work in droplets. Because you lose the advantages of miniaturization of the microscope. So what you have to do is a scale-out approach, in which you pass from a single droplet generator into running several of these in parallel. But this is only viable, or it's only a good option, if you can integrate these many devices in a single chip. And this is because a device like this, it requires some equipment to be run efficiently. And so if you want to run 500 or thousands of these, you will also need thousands of these equipments to be able to run. And so these technologies, they have to be cost effective in order to be competitive. So the challenge is to increase the small production and without increasing the number of connections and pressure pumps. So this is the solution that I came up, and I'm going to show you how like many droplets are being generated. Let me explain you that when you connect many of these droplet generators, and they all share connections. So this is a phenomenon called crosstalk. So what happens in one may affect the others because they're all connected together. So this is one of the largest, the biggest engineering challenges that we have in this technology. So I'm going to give you examples of problems with parallelization or with this scale-out approach in order for you to understand a little bit. So pressure drop in a microfluidic channel depends on the number of droplets that it contains. So let's look at this example. You have a microchannel and you have droplets. So when you plot the pressure, the pressure drop across this length, you'll see that the interface, you'll have spikes or increments in the pressure. And this is due to Laplace pressure jumps. Laplace pressure is just a phenomenon that happens due to the interfacial tension because you need to maintain this shape, right? So imagine this effect multiplied by hundreds of devices. So you'll have hundreds of microchannels, and then in each microchannel there will be different pressure drops. And then there will be the crosstalk that we were talking about. It might affect the droplet generation. So the second one is oscillatory pressure due to droplet generation. So this is like intrinsic property of droplet makers, is that when the droplet is formed, there is an increased pressure in these lateral inlets, and this will give you this increase in pressure. And then this will be oscillatory every time a droplet is pinched off. So you'll have pressure variations, like if your droplets are not completely synchronized. So imagine this problem, but times the number of devices that you would like to parallelize. Other problems are air bubbles, that they prevent liquids to reach the junctions, and fabrication defects or manufacturing errors. Like in this case, we have a debris here, which is like making the droplets to have polydispersed or different sizes. So imagine the same problems, but with hundreds of these. So now that you know all the problems that you may face doing this parallelization, let me explain you how I arrived to the solution that I show you. And first, we have to design or look for a droplet generator that is optimum for parallelization for this type of scale-out approach. So what will be the requirements of this droplet generator? So you have two main requirements. One is that the droplet size, when you generate the droplet size should be robust to slight pressure changes in the flow. And the second one is that you need to find a process in which you can replicate many copies of these systems. So for the reproducibility part, I did a literature review, and this is a good summary of all the different types of droplet generations systems that researchers have used, and I classify them into two. The top one here, they are done with planar fabrication methods like soft lithography, CNC micromachining, laser cutting, and things like that. And the bottom ones, they are made through the assembly of capillaries. So whereas in this case you have more control over the droplet formation, it is not viable to assemble many capillaries or thousands of capillaries to make a scale-out system. So we needed to go and pick one of those. So next, for robust operation, the design parameter that I was looking at, it was what characteristics can we use to improve the robustness on droplet generation. And I found this paper by Chan, in which they explain the effect of adding a step increment. So there is a channel height of 45 microns, and then there is a step of 90 microns. And this step is right after this cross junction. So here I'm plotting this graph to show you what's the effect of this step. So here you have the flow ratio, and here you have the capillary number, which is related to the velocity in the continuous space. So this region here shows you droplets. This region here shows you no droplets. So as you can see, with the step, or the top image, you have a wider range of capillary numbers in which you can generate droplets. Whereas in no step, this is very narrow. So the benefits for parallelization, that means that we can generate droplets even if there is variations in the capillary number. And the second parameter that I use for designing my devices is that I realized that the hydraulic resistance in a channel depends on the cross-sectional area. So different cross-sectional shapes, they will have different hydraulic resistance. And in fact, we have all these formulas, but an arbitrary shape is approximate to 2 times the viscosity times the length, and then the length of the channel, and then we have a relationship between perimeter square and area cube. So we have like all these geometries to try. And the hypothesis in this case was that maybe if we use different cross sections, we can have a device that will be robust for parallelization. And this is what we proposed and we made. This is a low focusing device or a cross junction. And then we add the step increment, the one that we were discussing. And we also add different cross sections in this junction. Right? So this one, for example, is a B group. We also add a wide and shallow. And we also another one that is like more standard, like more square-ish. And then we manufacture them. To manufacture them, I had to develop a process. This process was developed using PMMA layers or polymethyl methacrylate. So we start with PMMA layers of 1 millimeter, which are clean, and then we use a micromilling machine to cut the channels and make through holes, like in this case. So this is the finalized cutting, and then you can see the lateral view. So through holes, they pass through, and then you have your channel routings. It looks something like this. And we are able to create these geometries because we use milling bits of different tips and different shapes. And that's how we can produce these geometries. So this is SEM that shows you the micromachining. We measured the surface roughness, and it was lower than 250 nanos. And also I measure for all the channels that I made some variations in the fabrication, and the standard deviation was approximately 5%. We're not worried about this surface roughness because it's lower than the fabrication variations. So they'll have less impact than actually the fabrication variations. Well, once we have the mill channels, then we need to stack them. So we use alignment pins to put these 2 layers and put them together like this. So here you have the alignment pins, and then you have an interface. Then we use a tensile testing machine to exert some compression stress and to also heat the sample for to reach the temperature of fusion. So this tensile test is provided with some grips and with a chamber in which you can control the temperature. We put this device inside the chamber. We control the temperature to 150 C. And with this recipe, we're able to fusion these 2 layers, something like this. And then you have a monolithic device that you can connect holes to channels, right? And then, in order to interface it to the syringe pumps and the pressure pumps, we create some O-rings based on the same PMMA material, and we place those O-rings on top of the holes, and then we glue them with chloroform. And this is what the finalized device looks like. So with this process, we have developed a way of producing many copies because it is computer assisted. So you just make the drawings and then you can reproduce many times. And we also have made a process that is useful to create complex 3D structures. And by complex, I mean that you can stack many layers. So you can have different channels in different layers, and then you can interconnect them. So now, for device characterization, we use some pressure pumps. Then this is our devices. We use the pressure pumps to send the liquids to the device. And then you get these images using a microscope, this video. With software, we're able to measure the size of these droplets, and we ended up with this characterization. So here we're plotting the Weber number, which is related to the inertial effects, and the capillary number, which is related to the viscous effects. And we observed that there are two regions of droplet generation. The first region is the tripping regime. And in this regime, droplets occur at the interface here, at the cross section. And the second regime is called the jetting regime. And here, the inner phase strings into a jetting before droplet is making. So in this regime, in the dripping regime, droplet formation is much more stable. So we would like to study further these regimes, these flow regimes. So now we plot the diameter of the droplets against capillary number, and we compare the big group and the wide and shallow geometry. And what we observe is that there is a region in the wide and shallow geometry, like these red dots, in which the droplet size is almost constant to slightly flow variations. So now that means that you might have a good device that is robust to slightly flow variations that happens because of all the factors that I mentioned. In fact, when we plot the droplet diameter against oil and water flow rates, we see that for these two geometries, there is a clear relationship between the oil and water flow rate ratio and the size of the droplets. The larger is this ratio, the smaller the droplets. But whereas for this, we almost have a straight line, which is actually very beneficial. So this is the device in operation. And then we measure like the range of the dynamic range of the droplet formation. And we see that for these two devices, we have almost twice a big droplet sizes. Like you can create twice as much droplet sizes in the range. So now we have selected geometry, and now we need to use it to create some crystals. So we use the droplet generation, and then through the process that I explained before, we were able to crystallize some spherical agglomerates of glycine, which is a model in pharmaceutical manufacturing. These are the parameters of the crystallization. So this is to close the first section of my dissertation. So we developed a fabrication process in which we can reproduce or replicate many copies. And we also have multi-layer, so we can do stacks of channels. Then we also study droplet formation. We design different droplet generators with different cross sections. And we found that this one is a little bit more robust to flow variations. And it produces droplet sizes that are more or less stable. And the third part of this first section is we use this to crystallize active pharmaceutical ingredients. And we achieve the spherical agglomerates that is of interest to the big pharma companies. So now let me show you how we did the three-dimensional parallelization device on the scale-out process. So this section was published in Lab on Chip. And let's start by doing a review of the different technologies. So first, Lin was the first one to use fractal distribution network and to create some scale-up production volumes, 50 milliliter an hour. Then Nishizaku was the first one to parallelize over hundreds of generators. Then we have Romanowski in 2012, and he was the first one to create 3D structures, but he only parallelized like 15 generators because of problems with alignment. Then we have in 2013, Dangla. He was able to parallelize up to 256 generators, and he proposed a different droplet generator, which is based on confinement. Then we came us, and we actually at the time of the publication, we had the largest throughput, the largest production volumes, over a liter an hour. And we also had one of the most number of parallelized devices. But then this is like in the Olympics. Once you have proved something, somebody else comes after you and they take the throne. And these guys, they were able to parallelize 1,000 and achieve greater production rates. However, from all these designs, only these two, they explore a 3D for parallelization, for scaling out. And our design is actually far more scalable than this, because this is only one array in one plane. And whereas in our case, we will see how we can stack many of these arrays in a three-dimensional plane. So let's start off looking how I ended up with the device. So we have one droplet generator, and then the idea is that you connect two, parallelize it into two, then parallelize it into four, and then you get 8. And then another way of looking at this is by making, well, you need to connect them in one side, and then you need to connect the output in the other. So another way of looking at this array of generators is to organize them in a polar array. And then if we take a look at just the middle section for explanatory purposes, like this, then we decided, okay, how can we change this this configuration to make it more compact? And we came up with rearranging of the system. So now we can produce a device that looks something like this, that is actually shows you the 3D parallelization. So in this device, we have several layers. The one on top is just a cap layer, but then you have a dedicated distribution network for the continuous phase. Then you have a dedicated distribution network for the dispersed phase. And then you have a stack of generation layers. In this case, it's 2. So you can see them like here. This is how can you do. So from this, we needed to decide, okay, now we know how to rearrange, but what distribution network that can we use? So there are 2 types of distribution networks that have been used in parallelization devices. The first one, it's called a ladder-like distribution network, and this is because it looks like a ladder. So here you connect a wider channel, and you connect many of these devices. The second one is a fractal distribution, and in this distribution you have a point of a starting point that bifurcates into 2 and then into 2 successively until you reach all your connections. Examples of works that have been that use this type of distribution is this one by Romanowski and this one by Nishizaku. This is not exactly the same, but it's annular, so it kind of follows the same principles. So one thing we have for sure, that is that in order to provide the liquids to the bottom layers in this device, the vertical distribution network had to be something similar to a ladder-like. Like we cannot really manufacture fractal distributions in the vertical direction. And for that, Romanowski gave us a formula to design these distribution networks. And the idea is that you have different resistors here, and these resistors represent the hydraulic resistance of this feed line, and these resistors in parallel represent the hydraulic resistance of the shaft. And you want to select those resistors such as the pressure drop across this distribution network is less than 10% of the total distribution, of the total pressure loss. So for this, we use something like that. But what about the horizontal direction? What can we use for that? And we actually tried them all and because we were having some problems with some bubble trapping. And the one that worked was the fractal one. So now we have a multi-layer droplet generation that looks something like this, where we have the two dedicated horizontal networks or distribution networks that have this fractal distribution, and then we have vertical through-holes that have this sort of distribution. So we kind of combine the two strategies. And then we made droplet size with different amount of generation layers. So this is how we make this device. We mill one layer, another layer, we can mill n layers. And then on top of that, you have 2 layers for distribution and your cap layer, just like in this example. So if we use one layer, we have 128 generators. If we use 2 layers, then we parallelize 256, and 4 layers will give us like 512. You can add more layers to make more parallelization of these devices. So one characteristic of using this distribution is the fact that I realized that you can align all of these fractals or group them into petals. This is how I call them because of the similarity with the petal of a flower. So if you see this group of generators, they'll only share the liquid supply in one point, which is at the very beginning. And then apart from that, they never touch each other. So we see like, okay, this is a nice characteristic. Can we close sections of this device while we are operating? And the answer is this graph. So here we're plotting the normalized effective droplet diameter and the coefficient of variation. So coefficient of variation just tells you a number of the dispersion of the size. And we get these two quantities for a full device. Then what happens if we close one petal and then adjust the flow rate so that they operate in the same regime? And you see that there is not much change. So we close 2 and 3 petals, and we can see that there is almost no change in the droplet diameter and nor in the coefficient of variation. So because of this characteristic, now we can have a device that can adjust to production volumes. So you can close sections or open sections as you need. And for this characteristic, I should have called them, instead of a petal, a clover, because they were the clover of good luck. Okay, so this is the video of the device working. You can see the flow distribution across all of these droplet generators is equal, and then we are producing large quantities. So we characterize the emulsions that we generate, these droplets that we generate, using this setup. Here we slide the emulsions through a surface that is lighted from the bottom, and we take images of the droplets as they slide through. And then we use software, MATLAB software, to characterize and to get statistical information of approximately 8,000 samples or 8,000 droplets, and we get these size distributions. So devices with 128, 256, and 512 were characterized And here I'm plotting the coefficient of variation in droplet size against the dispersed phase flow rate per layer. And then I'm showing you like this is 256 generators and some 70. So one thing that we notice though is that when we add layers to this stack, we don't notice a relationship with the coefficient of variation. Actually, the device that had the less variation was the one 256 and not the one with only a single layer. And we also notice that the fabrication variation have much more influence. So you can see that the 256 was the device with less fabrication variation and also the one that produced the less coefficient of variation. We achieved coefficient of variations for this device up to 6%, which is like huge improvement compared to the way that pharmaceuticals create their crystals. And the other characterizations that we did is we plot now here the effective droplet diameter against the total dispersed phase that you can generate in the devices, and we achieved production volumes up to 1 liter an hour, and we were able to parallelize up to 512 of these generators. So this is not the only thing that we can create. It's not only 1 liter an hour. Or the fabrication of our devices can withstand high pressures up to 7.5 bars, and we can stack at least 10 generation layers, which will give us production volumes up to higher than 3 liters per hour. So are these volumes relevant? Are these volumes relevant to commercial applications? So not for all applications, definitely. So for like aspirins, maybe it's not a good option. But what about low-dose pharmaceuticals? For those pharmaceuticals, actually 1 to 3 liters an hour makes a lot of sense. I'll show you why. So I made this table based on these two guys, the World Health Organization, who provide me the number of people affected by these diseases. These diseases are chronic diseases, so you have to consume pharmaceuticals continuously. And then in this book that discusses low drug formulation, we get the name of all these commercial drugs, right? And then we see that the active pharmaceutical ingredients per tablet is in the range of a few milligrams to micrograms. So with 1 liter an hour of our devices, we can create up to 625,000 of these Mavic tablets. And you can create, even in some cases, millions of tablets in 1 hour. So now we ask this question: how many devices do we need to provide all these people 1 tablet a day? And this is the answer. You can see, like, for some cases, 66 to 263, but some others, you only need 1 device, 1 to 5 devices. So this really makes a lot of difference, and you can see that we can use this technology to produce pharmaceuticals that require low variability. So this is now the third section of my defense, and then we're going to discuss some on-chip monitoring. And this was published also in Lab on a Chip, and we got the cover image because of the work. So now we have seen how we can use droplet as microreactors. We have crystallized some pharmaceuticals. We have made a scale-out system that integrates hundreds of these devices. And then we all have also seen that we need probably to run few of these devices if you want to serve the market, or you want to give 1 tablet a day to everyone. So we need some sort of monitoring systems that can look at the production of these particles. And this is what this chapter is about. So some production errors that may happen is like you have your device running on your stable operation, right? But if you have one of these problems, like problems with the liquid supply, or if you have clogging, aggressive fouling of your microreactors, or fluid liquid leakages, air, or anything, then you can pass from stable droplet generation to something that looks like this. And the implication of having these errors is that you generate polydispersed output, and then this output will contaminate the production that you made before. So you don't want to contaminate your finalized products. Remember, these devices are connected in a continuous, they are running in a continuous fashion. So there is, from liquid supply to crystallization, a continuous workflow. You don't want to contaminate. So one way of doing the monitoring will be to use cameras and computer power, like we did for characterization. However, for this we will need several cameras and several optics, and also computers to run these monitoring systems. So what about electrical sensing? Can we use electrical sensing to monitor total production? And the answer is yes, maybe. If we are able to look at the electric properties of the emulsion. So these are the electric properties of different materials. PMMA is the substrate, or the material that we use to build the chips. Water and dodecane are the two phases that we are running to generate these emulsions. So you can see that the permittivity of water compared to oil is very large. It's a huge difference. So if we look at the permittivity of a complex material, such as this combination of different materials, where you have PMMA, you have water, and you have oil, then maybe you are able to detect how much of water is in oil, just because oil and PMMA, they have similar permittivities, and water has much. So the effective permittivity of this material will depend on contributions or on the proportions of the others, of the individual materials. And then there are other dielectric properties in this type of complex emulsion. So the dielectric properties will depend on different parameters. So one is the permittivities of the individual fluids. The other one will be the water cut, which is the volume fraction of water in the oil. Then you can have effects such as flocculation, coalescence, the shape. All of that affect the permittivity and the frequency in which you take the measurements. So the idea is that you want to detect from droplet generation that is stable to something that fails, that looks something that like this. So the bad news is that you have a bunch of effects that may change the dielectric properties of the emulsion, but the good news is that the dielectric properties of the emulsions are kept constant as long as you have a stable droplet generation. And then, in order to measure the dielectric properties, we design some capacitive and radio frequency sensors. Here, this table compares the two. So for the capacitive sensors, we can directly measure the reactive part of the impedance with an LCR meter. And then you can effectively measure capacitance in ranges, well, it should be few hertz to megahertz. And you need the number of channels that you need to read. You need an instrument per channel. And the RF resonators, or the RF sensors, you cannot, at RF frequencies, you cannot really measure this impedance, or instead you measure the S parameters, which is power reflected and transmitted from one port to another. And the advantages is that you can measure the dielectric properties at much higher frequencies in the gigahertz range, and you can integrate multiple of these sensors in a single readout. So how do we simulate the errors in droplet production? So this is our device, and we took a section of this device and we manufactured like to be able to manipulate. We did this connection, the one on top right. So we have droplet generation here. Then we have tubing that goes to the sensors. And then by poking and moving the tubings here, we are able to produce errors in the manufacturing process. Errors that look something like this. So the first one is a capacitive sensor. And here we use the parallel plate equation in order to design these sensors. So we see that the parallel plate equation depends on the effective permittivity times the overlapping area over the distance between these two electrodes. And these parameters or these conditions actually made us design a very wide and shallow channel in order to detect measurable capacitance. So it's something like that looks like that. So now we send the emulsions through the inlet. The emulsions are read in this. The dielectric properties of the emulsions are read in this capacitor, and then there is an output. So you have a system that looks like this. So we measure a channel full of water, and this is the capacitance that we obtain. We measure a channel full of oil, in this case dodecane, and this is the capacitance that we obtain. So our emulsions, as they are like, as their dielectric properties depend on the volume fraction of one to the other fluids, then we'll have a capacitance in this range. So now imagine this is how we can use these measurements in monitoring purposes. So imagine you are monitoring stable droplet generation, and it has a capacitance that is stable, that looks something like this. And then, for some reason, your device failed, and they start producing polo dispersed output. Then you'll see a shift in the capacitance that will send an alarm, and then you can take a corrective action. You can stop, you can automate to try to avoid this polydispersed undesirable product to reach to further down the line of production. So the second sensor that we designed is an RF resonator, and here we use RF means radio frequency. So here now we are using frequencies in the gigahertz range. And the T resonator is a microwave circuit that is formed by some metal lines that have the shape of a T. So this one here is the feed line, and this one is a stop. You can see it in in this picture. And then we have two ports. We send signals, a sweep of frequencies through one port, and we measure the reflective and the transmitted power through these ports. And then when the sensor resonates, there is a frequency notch that looks something like this. And then it has harmonics, and these harmonics occur at odd integers, multiples of the quarter wavelength. And the formula that we use to design these sensors is given by this formula here. And here we can observe that the length of the stop here is inversely proportional to the frequency. So we can actually change the length. By changing the length, you can design sensors that operate at different resonance frequencies. And this is what we did. So we created sensors with 8 millimeters in length and sensors with 60 millimeters in length. And then when we fill the channels with water, this is the type of response that we get. So we get two notches. When we fill them with dodecane, this is what we get. We get a shift in these parameters. Then we plot again air, just in case sometimes you have leakages, and you also have this shift. So the dynamic range or the dynamic of detection of this sensor, that is this longer resonator, is given by this area that you have here. And then for a smaller resonator, the the dynamic range is given by this area. So emulsions will have a response that is somewhere in the middle of these ranges. So how can we use this now to monitor our production? It's like, okay, so we have these sensors that are looking at this stable droplet generation. So we have 2 frequency notches. Then one of them fails, or you send this type of throughput, and then there is a shift in the frequency of the one that failed. And with that, you're able to actually corroborate that these two are independent from each other. So if this one fails, there is this shift. If this one fails, there is this shift. And this means that we can design resonators or take measurements of different resonators with a single device, because the transmission line is very wide. And then you can design different resonators at different frequencies, and they operate independently. So when we normalize the value of the sensitivity of these sensors, we see that they have actually similar sensitivities. We normalize these values to the original frequency, the frequency at which they were designed, and in the capacitance they are normalized to the capacitance that they are designed. So for emulsions ranging from 10 or 11% to 33, you have more or less a 10% variation in the signal that you are reading. And these two are similar, and this is because they both just measure impedance. They are both based on the impedance measurements. So the conclusion is that now we have seen 2 sensors that actually were able to detect changes in the water in oil concentration up to 2.4%, and these are the sensitivities. They are comparable. In design, the RF resonators are more simple to design because they allow us to design channel dimensions that are more less wide and shallow. You can generate other type of geometries and still get a reliable signal. Then, in the sense of operation, we see that because we have 2 notches, we can have other notches as well, and then we can measure different channels with a single readout device or a single device. So future work. So this is what we have achieved. So this is droplet production at large scales, and we can probably incorporate this type of microreaction technologies where you have different liquid streams or different reagents coming to a point, and then you have droplet formation. But we cannot incorporate these 2 other type of microreaction technologies in which you have droplet merging. So how can we achieve or may achieve this? Is by using one of these lock and break mechanism or droplet generators that were designed by Wong-Stein. And in these cases, you have your device that has some bypasses, and then the dispersed phase meets the continuous phase and gets into this cavity. Gradually starts growing and is starting to close the bypass channels. When it closes the bypass channels, then droplet formation happens. So here I simulated different of these devices at different oil and water flow ratios. And what I observed is that droplets are of the same size, no matter the oil and water ratio, and also that you can control the frequency of generation. So 1-on-1 will give you a higher frequency of generation than one that has 5-to-1. You can see that there will be 5 times more oil, more spacing between the droplets. So, and then we can use droplet merger, like the one designed by Professor Di Mello. And here we have a device that waits for the next droplet to arrive to start the fusion and do the microreaction downstream. So if we combine this generation and this type of droplet merger with or scale out device, we might be able to parallelize systems that have these characteristics of droplet merging. So for conclusions, I studied different geometries for droplet generation, and I selected the one that worked the best for parallelization. Then we created, or I created different devices with 128, 256, and 500 generators. We demonstrated production volumes over a liter an hour and coefficient of variations of approximately 6%. We show how we can use these distribution networks to organize our devices in petals and how we can close them. And then we have also demonstrated the use of these devices in pharmaceutical manufacturing of some active pharmaceutical ingredients. And we see how these quantities make sense for certain applications. Then we show capacitive sensors and RF resonators, although both have similar sensitivities. The resonators allow us to parallelize the readouts or to parallelize the monitoring, so we can monitor more channels. And the good news is that these sensors can be integrated into the device, and then by doing so, then you can have an integrated device with production and monitoring. So finally, for conclusions, so we have worked with droplet generation, scale out, with monitoring systems, and our collaborators in Singapore are working with the scale out processing of these technologies. And the combination of these might give a good future for these technologies for the development of commercial products. So these are the contributions that I offer that I published in this work. These are 2 journal covers that I was fortunate to be in. And then these are other publications from my work along my PhD, which are not related to this, but with other side projects. And then for acknowledgements, it is hard enough out there, and get all the help you can. And by doing so, it's just part of that lifelong search for wisdom. This is a phrase that was made by Phil Knight. He is the CEO and former of Nike. And I really like it because it really expresses the feelings that you get when you're doing a PhD. Like sometimes you're frustrated, but you have people to help you. And then there is a mistake because there was a slide that I didn't include, in which I show many pictures of people that I wanted to thank, especially the professors, the ones that are present, and Professor Kant. Let me just write it out. It's just that we have some issues with the thing, and then I didn't include it. So all these people really helped me a lot. The professors here, Ian, thank you for giving the opportunity of doing a PhD. My co-supervisors, thank you for all the advice. Professor Khan, he's our collaborator in Singapore, helped us with the crystals. Thank you so much. The nano fabrication guys here in KAUST, it's been a great time to work with them. Our groups, my groups in here, the Empire Lab, the one in Singapore, and the SMM, you have been very nice to me. I really enjoyed working with them. And especially I want to thank David Castro and Arpis. These are my colleagues from the Empire Lab. Without them, I think this wouldn't have been possible. All my friends that are an important part in my life here at KAUST. And finally, to the king, because like he gave me this opportunity. And finally, I would like to thank my family, my parents, my wife, and my brothers and niece for all the support that they give me through these years. My father, he passed away last year, and he couldn't watch this presentation, but he was suffering from COPD, just a respiratory disease that I explained. And I really hope that this work may bring technologies that can produce better pharmaceuticals to the access of all of us. And with that, the next slide was thank you.
Thank you, David. So we'll move on to a very brief question period from the audience, if anyone in the audience would like to ask a question, and then we'll move to the closed session where the professors are welcome. Is there anyone that want to ask a question? No questions. It was explanatory. Excellent. Okay, so then we will kick all of you out. Enjoy the rest of your afternoon, and we will then get to grilling David momentarily. Yeah, me too.
Muchas gracias.